Now, homogeneous functions. A function of several variables, I'll just use 2, is homogeneous if, when you multiply each of the variables by the same constant, in other words, if I do the function operating on t times x and t times y, if that produces the original function again, only multiplied by some power of that constant that was used. And if that's the case, it's said to be homogeneous of degree n. For instance, take this function here. If I was to do the function acting on tx and ty, I would have tx squared and ty squared, which multiplies out to t squared x squared, t squared y squared, and factorises out to t squared x squared plus y squared, which is just t squared times the original function. So that would be a homogeneous function of degree 2. Another one. This one here. Is this homogeneous? Well, let's have a try at it then. So if I multiply each of the variables by the same constant t, what would happen? Well, this says I'm going to do power 8 of the x and 3 times power 8 of the y over 2 times t times the x, t times the y. So taking that out, I've got t to the 8, x to the 8, 3t to the 8, y to the 8 over 2t squared xy. Now taking out those t to the 8s, I've got t to the 8, oops, almost forgot that wee bitty, over, I'll just put that first, 2t squared, t squared 2xy, and then cancelling it down, I've got t to the 6 times that thing, well, I'll just write it again, x to the 8 plus 3y to the 8 over 2xy, which of course is just the original function. Which means again, that was homogeneous, because I've ended up with the same function I've started with, of degree 6. Another one. I could go on all day doing this. This one then, is this homogeneous? Well, let's try multiplying it. So I would have t to the x cubed, 3 times t to the x, t times y, over t times y cubed. And that multiplies out to t cubed x cubed plus 3t squared xy over t cubed y cubed. Factorising that out, I've got, I can only take out t squared this time, leaving me with tx cubed plus 3xy over t cubed y cubed, which is t to the negative 1 tx cubed plus 3xy over y cubed, which isn't homogeneous to degree 1 because that's not the same as the original function. The x cubed term has been corrupted there, and that wasn't constant throughout. So this one is not homogeneous. Now, all of those, or rather these ones here, were homogeneous, and you could spot it almost straight away because there was a balance in the powers. It was x squared power 2 power 2. The top part was power 8 power 8. The bottom involved a power 2, but the top and the bottoms were balanced independently, and that produced a homogeneous equation, whereas there wasn't a balance in the top part here. It was a power 3 and a power 2. When you've got a balance in the powers in the parts, you'll have a homogeneous function. But the best homogeneous functions are the ones of degree 0. So this one here, again, it's certainly homogeneous because I've got a balance in the powers of the part, power 2, but the bottom is also power 2. So I'm going to give that a little test. What have I got? If I multiply each of the variables by the same constant, I'll have what? I'll have t times x squared plus t y squared over tx ty. Multiplying them out first, tx squared, t squared x squared, t squared y squared, t squared xy. Factorising it out, do you need to spell it out? Well, I'll go ahead and do it. t squared times x squared plus y squared over t squared times xy. That cancels out and just leaves x squared plus y squared over xy. Exactly the same as the function you started with. This is homogeneous of degree 0. And that's a handy one because you end up with exactly the same value. That says if you multiply the variables by the same amount, the answer remains unchanged. If you have to think of a graph of that, or you're moving out along rays where you'd be multiplying each of the variables by the same number, you'd have the same value radiating out from the origin. But it's not that that's the interesting part here as far as differential equations are concerned. It's the fact that if you end up with the same, it means not only were the powers balanced, but the powers were the same in all the parts. You had an equality of the powers in all of the terms. Degree 0, an equality of the power in every single term. Power 2, power 2, power 2 for this particular example. And if that's the case, there's something you can do with it then. You could rearrange this jumble of mixed terms, which would be difficult to separate in a first order differential equation, into a single variable instead. And then you've got one that's easily separable, simply by dividing everything by x squared, for instance. If I divide everything by x squared, I'll have x squared over x squared plus y squared over x squared over xy over x squared, which is 1 plus y over x squared over y over x, which could be rewritten with a change of variable to 1 plus v squared over v if I used let v equal y upon x. Now the function is expressed just in terms of v's in this part of it. Of course, if it was a differential equation, then I would have to rearrange my dy by dx in terms of that. But that simply means taking y equals vx and differentiating both parts. Now, there's no more space here, so what I'll do is we'll go back up to the top and solve the differential equation that would be given by dy by dx equals x squared plus y squared over xy. By recognising it's a homogeneous function, balance of the equality of the powers in all of the terms, meaning I can change it with a change of variable into just an expression in a single variable, and then it will be separable. So we'll do that again up here. So back to this. Solving this first order differential equation, which turns out to be a homogeneous function. So that means I can rewrite that. If I rewrite that as dividing it by x squared, 1 plus y over x, all squared, over y over x, I can rewrite that as 1 plus v squared over v if I do this. If I let v equal y upon x. If you've got a homogeneous function of degree 0, you can rewrite it in terms of a single variable. Now, I'll need to replace this dy by dx, so I'll rewrite that then. So y is going to equal vx. So differentiating both sides with respect to x, I would have, now I've got a product rule, so I would have differentiating that would be dv by dx times x, plus differentiating the x part now, just leaving v. So dy by dx would be this part here. So I can replace all of this. Instead of dy by dx, we have to put the x in front. I've got x dv by dx plus v is equal to 1 plus v squared over v. Eminently separable. So I've got x dv by dx, that's the x's on the one side there, equals 1 plus v squared over v minus v. Putting that into a single fraction, I'm going to have 1 plus v squared minus v squared, so that's just going to be 1 over v. Separate them now, v dv equals dx over x. Integrating them up, a half v squared is going to be ln x plus c, or I could absorb that into that and make it ln, and if that could be written as the log of something, then that could I'd multiply that, so I'll make it ln of, but I'll still just call it c because it's not been evaluated yet, so it's still just some constant. Then, what was v? v was y upon x, so I've got half of y squared upon x squared equals ln cx. And then finally, y squared equals 2x squared ln, and I'll just leave that as ln(c)(x). Right, that was that one. Now let's try a longer example then. So, trying this, a more meaty example then of a first order differential equation. Let's just sort it out first of all into dy by dx. So, dy by dx would have to be, taking this over and reading it across that way, dy by dx would be 4y minus 3x over 2x minus y. And then straight away you can spot, okay, the terms are jumbled up, not so easy to separate, but you've got an equality in the powers of all of the terms. They're all power 1, which means that I can do this then. I can rewrite that as dividing everything by x, 4y upon x, and that'll just be minus 3, and that'll just be 2 minus y upon x, and then I can let v equal y upon x, and then rearranging that, y equals vx, so dy by dx is going to be x dv by dx, differentiating that term, plus the second part using the product rule, v. So now I can back over here. So I've got x dv by dx plus v equals 4v minus 3 over 2 minus v. Then I'll just take that over and make this into a single fraction. So x dv by dx is going to be over 2 minus v. I'll have 4v minus 3. Now subtracting the v, but putting it into this, will be minus v times 2 minus v. So what's that lot going to tidy up to then? So I've got plus v squared minus 2v plus 4v. So I've got v squared plus 2v minus 3. And it is. So that part can join that, and that part go on the other side. So I've got 2 minus v over v squared plus 2v minus 3 dv equals dx over x. Now it's ready to go. Now I can just integrate both sides. So that's a simple, takes you back to log. And in this one here, unfortunately, that's spoiled because that's not just derivative of the bottom, so I'll have to use partial fractions in that bit. That's going to be partial fraction bit at the top here. 2 minus v over, might as well factorise it, because that's going to be v1, 3 plus the 3 minus the other. So if that was to be equal to a over v minus 1 plus b over v plus 3, then a times v plus 3 and b times v minus 1 would equal 2 minus v. Then in whichever way you like, equating the parts or just using knockout values, just use knockout values. If I take v equal to 1, knocks that out and makes that part into 4a equals 1. So a is going to be a quarter. And if v equals, let's say, negative 3, then that knocks out. And I've got negative 4b equals 5, so b is going to be negative 5 upon 4. So I could put that back down here as the integral of these two parts. I've got 1 over 4 times v minus 1 minus 5 upon 4 of v plus 3. dv is the integral of dx upon x. I better take this up here. So going up to here, I'm going to have, integrating the two parts, I'm going to have 1 upon 4, a quarter of ln v minus 1, minus 5 upon 4 ln v plus 3 is equal to ln x plus some constant. I'm just going to pop that inside there in the next stage. Well, I could take the quarter out and put it over the other side, so it's going to be 4 times ln of, I'll just call that again c inside it. Well, c's not been evaluated yet, so I'll just still use the letter c to stand for this thing requiring working out. And that part then is going to have, subtracting these logs will be a division, but I need to pop that inside as a power 5. ln of v minus 1 over v plus 3 to the power 5 is equal to that. Should have popped that 4 up there at the same time. So I'll pop that 4 up there and then remove those logs. So I've got v minus 1 over v plus 3 to the power 5. is equal to, and then c, which you could leave as just again another c, so cx to the power 4. Now I've popped off those little raincoats just now because there'll be some values that will render these logarithms valid, but I'm just going to leave it out just now because of that. I've got a positive part here anyway. Now what have I got? I'll need to put that back the way it was. That's what it is. Here it is. V should have been y over x. So I've got y over x minus 1 over y over x plus 3 to a nasty power 5 is cx to the 4. Now I need to render that into a normal rational expression, so I could take 1 over x out of the top, leaving it as y minus x. I could take 1 over x out of the bottom, leaving a y plus 3x, but when that pops out the bracket it'll be 1 over x to the power 5 times a y plus 3x to the power 5 equals cx to the 4. Now that would cancel down to an x to the 4 on top, and that x to the 4 will cancel out that x to the 4, so now I'm down to y minus x over y plus 3x to the power 5 just equals c, and then finally I could just write it as y minus x equals c times y plus 3x to the power 5 for certain values of x and y. Now I've cleared that. I'm not going to stop because maybe just for a wee bit of fun we'll just check if that is in fact correct by differentiating it and see if it goes back to there, ignoring the fact that I've left off the overcoats there. I've left off the absolute values without justifying the values that actually give you that. So does that go back to that? Well, that should be true for any value of c, so let's just take the simplest one, c is 1. So I've got y minus x is equal to y plus 3x to the power 5 differentiated. So differentiating this side, dy by dx minus 1 would be 5 times y plus 3x to the power 4 multiplied by the derivative of the inside, which is going to be dy by dx plus 3. I'll separate that out, I think, first of all. Dy by dx minus 1 is going to be, first of all, it's going to be 5y plus 3x to the 4 dy by dx plus 15y plus 3x to the 4. That's looking a bit nasty with these y plus 3x to the 4s, which don't appear anywhere here. I'll take over to one side. So I've got, put my dy by dx's together on this side. I've got dy by dx minus this. I shouldn't really have written this line out because I could have gathered it at the same time, equals 1 plus that, y plus 3x to the 4. So I've got 1 minus, again I should have gone one step ahead because it's getting tedious writing this all out, dy by dx is 1 plus 15y plus 3x to the 4. So finally, dy by dx equals 1 plus 15y plus 3x to the 4 divided by 1 minus 5 times y plus 3x to the 4. It doesn't look anything like that because I can still change it using this, because this says y plus 3x to the power 5 should equal that. So for that part, y plus 3x to the power 4, remember that's a 1, would be y minus x divided by y plus 3x. So I can replace those parts. So I've got 1 plus 15 times y minus x over y plus 3x over 1 minus 5 times y minus x over y plus 3x. We don't have enough room to finish it off. Multiply everything by y plus 3x to resolve it into a proper rational function. So I've got y plus 3x plus 15 times y minus x over y plus 3x minus 5 times y minus x. And then tidying that part up, unfortunately there's not really enough room, so I'll have got up to here. I've got y plus 3x plus 15y minus 15x over y plus 3x minus 5y plus 5x. So we'll put the y terms first here, so I've got 16y minus 12x over, put the x term first here, 8x minus 4y, dividing everything by 4, and I've got 4y minus 3x over 2x minus y. Exactly the same. Ta-da! And there it is.